Hi all, welcome back to Cracking the FAANG interviews. Today I'm going to be talking about the problem where we've been asked to find the kth smallest element in a binary search tree. And just want to emphasize, this is a very popular interview question that's been asked at Amazon, Google, and Apple. And the question is available on Leetcode. The number is 230, so you can check it out. It's the link is in the description. Let's look at the problem in more detail and just try to triage it. We've been asked to find the kth smallest element in the binary search tree, and we've been given a binary search tree here. It's not a binary tree. So quickly, recapping, binary tree has at max 2 children for every node in the tree at max. The binary search tree is a binary tree with a special property for searching where all the nodes on the left side of the tree are less than equal to the root node, and all the nodes on the right side are greater than root node, which makes it very efficient for searching. And again, this is a tree search problem. The search query, if you want to think about it that way, that's been given to you is to find the kth smallest element. So let's look at this example. We've been given this tree and we've been asked to find the smallest element. K is 1 indexed as given in the question. So the smallest element in this case is 1. So we return 1. Let's look at another example to make the idea more concrete. So in this example, we've been given this tree. We've been asked to find the third smallest element. So by just looking at the tree, the first smallest element is 1. The second smallest element is 2. The third smallest element is 3, and we return 3. And as I said, this is a binary search tree. The way I would approach the problem, again, since it's a tree or graph problem, the first thing that comes to mind is traversal. And there are many methods for tree traversal. The first one is BFS. The second one is DFS. The third one is pre-order traversal. The fourth one is in order. Fifth one is post order. If you haven't already looked up or are not familiar with these methods, I'd encourage you to pause the video right here. Maybe quickly look at these algorithms, and I'll have videos for this coming up soon, so I'll link them in the description. Check the links out. But let's try to quickly go through these and figure out which one is ideal for our current problem. So what we do in breadth first search is we go level by level and we search for what we are looking for. But here you're looking for kth smallest. If I even go level by level, there's no way in which I'd know what, no way I'm exploiting the property of the search tree, where it says the left node is less than equal to and the right node is greater. So that's breadth first search. Let's see if we can apply depth first search. So if we do that, we'll be traversing in the depth direction. So we'll go all the way down, come back, go on the right side, go back, then go on the once we are done with the left side, you go on the right side. So that's another way of traversal. Again, we are not really able to search or exploit the property of the left side being less than equal to and the right side greater than. So whenever you're given a sorted tree or a binary search tree, as the question calls it, you should think about these three methods that I've highlighted here: the pre-order, in-order, and post-order. What pre-order essentially does, to quickly summarize, is it's going to first look at the node, then go to the left side and the right side. So in this case, it's going to look at 5, print 5, then go all the way to the left till the all the way till left ends, go print 1, come back, print 2. Since there is no right child here, go to 2, which essentially becomes the node, and so on. But let's try in order next, and figure out if that sort of tells us the kth smallest by itself. So in order, what you do is you first go to the left side all the way, then print the node, and then go to the right side. So we are here at root, so we go to the left side all the way, we print 1, and again 1 is the smallest. As you can see, this is a binary search tree. The leftmost tail is always the smallest. Then we take a step back in the recursion, we go to 2, we print the node 2, and 2 is the second smallest. As you can see, there's no right child. We simply return here and go back to the node that called 2, and now we print the node, which is 3. And as you can see, we are actually traversing the array in sorted order. By simply picking one of these traversal methods which sort of fit the problem statement, you have the tools that you need to be able to execute your search query efficiently. And the work done in all of these algorithms is pretty much the same. The only difference between them is the order in which you traverse or search your tree. So as we can see, in order clearly works for us. It's giving us a sorted array. Now the challenge is to find kth sorted. How would we do that? So the idea is we as we traverse, we keep a counter which says, okay, this is the first element I hit, so this is the first sorted. And when you go to the second element, which is the node in this case, you say, okay, and you print. So whenever you print or sort of go to a node, you increment your counter. So you go to the second sorted, or you can also decrement, but for simplicity, let's just think of incrementing. You're at the second sorted, and here since k is 3, the third step you take and you get to a node is the third sorted element, third smallest element. So you can simply print that node. So if the idea has become concrete, I'm going to jump into the code and talk about it further. We've picked in order traversal as our candidate. And what I'm going to do is start with the temp count. In this case, I'm decrementing. Unlike increment that I talked about in the example, but you can go both routes. I've just tried to keep this simple, because when you decrement, if I've been given 3, I decrement it to 2, 1, and as soon as it becomes 0, I mean it means I've hit the minimum. And since I am 0 indexing it, I start with k minus 1 instead of k. That's the reason of having this as k minus 1. And I write this function for in order traversal. So just to recap, in order traversal for a binary search tree gives us a sorted list, I'd call it. So first step is the base case. As soon as you hit a node or something that does not exist, you simply return float minus infinity. This, you can think of this as an error signal for us. It can also be a value -1 if the tree does not contain -1. So we just take an absurdly large negative value for our error signal. It means there's nothing here that you want to report. The first thing you do is you go to the left side, as we discussed earlier. So the first recursive call is just go to the left side and find the left value, which could be minus infinity, again an error signal. And if the left is not the error signal, meaning you have actually found value, something is being returned which is not an error signal, so you simply stop and just start returning there. So you'd have your tree, and you found the first minimum. If you're looking for second minimum, if you found your first minimum, you go to the parent node. This is the second minimum. You know your k has become 0. You simply start returning the value. You don't even make this call on the right side because you found your what you were looking for. So the next statement here is actually checking for when to start returning. The first one was the error code. The second is actually returning the value. And if you have not hit 0 on your temp counter, you essentially decrement your temp counter further. Meaning what I mean by that is, if you're looking for case 2, you start with k minus 1, which is 1. So this is 1. You don't find what you're looking for here. K is still 1. You decrement k, so you make it k minus 1 minus 1, which is 0 here on this node. So this is your second minimum. This is the step that helps you decrement and move from the lower node to the parent node. And the third step is to actually do the right traversal. Again, remember, in order traversal goes by this: you first visit the left wing, you process the node, you look at this node, and then you go to the right wing, and in the end what you do is you just return the max. So if there's an error signal coming, minus infinity, you just ignore it, and you'd pick the other side and simply return that. So the time complexity of this would be, in the worst case, you could have a tree which sort of looks like this, where the elements are 3 to 1, and again this is a binary search tree. It's a valid binary search tree, even though it looks like a linked list, and it's a worst case of a tree. So the time complexity in this case would be O of n, and again the space complexity would be O of n, because this is the worst case of a skewed tree. I hope the idea was clear. Please, thank you for watching Cracking the FAANG interviews. Please like, share, and subscribe for more exclusive interview content.